If everything has gone according to plan, you should now have something that looks like equation 617 in the book, except that your right-hand side is a little different. Now, let's try to take a look at how 617 looks in the book. So for I ranging from 1 to n and j ranging from 1 to m, the finite difference approximation of the problem looks as such. Minus lambda squared times ui plus 1 comma j plus 2 times 1 plus lambda squared times ui comma j plus, no, not plus, minus minus lambda squared ui minus 1 comma j minus ui comma j plus 1 minus ui comma j minus 1 is equal to 0. Now for your case, your right hand side might not be 0, so I'll just put a question mark over here. But in the book it's 0, and for you it should be something else. Okay, so when we look at this, well, one of the first things we should probably notice is that this equation contains indexes I plus 1, I, and I minus 1, and it also contains the indexes j, j plus 1, and j minus 1. So why is that a problem? Well, it varies a lot in both indexes. And actually, if we take a look at this, we will need to solve all m times n equations. So for each I and j we fix, this will be a specific equation, and I can go from 1 to n and j can go from 1 to m. So we have here, we actually have m times n equations, and if we want to solve these equations, we will need to solve all m times n equations in one go. So we have to solve them at once. And this calls for a matrix equation. Now, since we need to solve all of this in one go, the nice part of this is that once we have our matrix equation, this whole Poisson equation, finite difference solution, just all boils down to solving one matrix equation. A huge matrix equation, but it all boils down to, code-wise, just solving one matrix equation. So that is very nice. And, well, just notice that this method is quite clearly implicit. So, because some of you have been asking me about, well, how do I see if a method is implicit or explicit? Well, first of all, if you need to find all of the values in one go, then quite clearly it is implicit. So that is one of the ways you can recognize an implicit method. The problem here is that for us it's a bit hard to do this, to solve all the equations at once, because you kind of start asking yourself, well, how do I write up this matrix equation? Because, well, first of all, in the earlier chapters when we had matrix equations, it wasn't in the same kind of, it wasn't the same type of finite difference approximation as we have here. In the earlier chapters, for example, with maybe the heat equation, let's say, or the advection equation or whatever, in the earlier chapters, we just iterated over j. We would normally say, okay, for j equal to 0, I know something. I know an initial condition. So I know the value of ui for j equal to 0. So this is how it looked in the earlier chapters. And then we just solved you know, a matrix equation for j equals 1 based on something where, you know, j equal to 0 was on the other side, and then we would find all of the ui for j equal 1, and then we could find all of the ui for j equals 2, etc., etc., etc. But we can't do that here. Because we can't just take all of the parts where we have j and put them on one side, and all of the parts we have j plus 1 and put them on the other side. And the reason we can't do that is because we also have j minus 1. So we have both j minus 1, j, and j plus 1. And the reason why we have that is because we worked with center differences, and also because in both the time and the space dimension we have boundary conditions and not just initial or terminal conditions. So that means we'll have to think up another method. So we need to solve, again I repeat, we need to solve all m times n equations at once. So what does that actually mean? Well, let me just try to draw up the grid again. So if this is my grid, and I have the shaded dots out here, so I'm kind of doing a stencil right now, where I know the values of u in the boundary of the unit square, because these values are just equal to 0. Well then, based on the fact that I know these dots out here, I will need to find the value of whatever I have inside here. And if let's just draw a few more dots out here. The thing is, for example, in this example case where I have drawn 1, 2, 3, 4, 5, so n is equal to 5, and 1, 2, 3, 4, 5, m is equal to 5. So in the case where n is equal to 5 and m is equal to 5, well, I actually have to solve, well, I'm going to have to draw a lot of dots in here, but I actually have to solve blah blah blah, etc., etc. I have to solve 25 equations governing the value of u on these dots here. I have to solve 25 equations at once. And you kind of start thinking, well, I want something that kind of looks like AU equal to B, right? But how should A look if I have 25 equations, and which parts of A should correspond to the I's and which part should correspond to the J's? And the answer to that is, well, we can do this by using a different kind of ordering than we have in 617. So basically the way we switch to matrix equations in the book is by looking at page 190 to 191. Now you can just skip this video already and just read 190 to 191, and once you've understood that, then you're good to go. But if you want to just understand a little bit more of the intuition, then you can continue here. So essentially what we want is we want to end up with equation 619. So the answer is more or less already given. We want to go from what we have in 617, which looks like this, and we want to change into what we have in 619, where we index by L instead. So where we have minus lambda times V L plus 1 plus 2, 1 plus lambda squared VL minus lambda squared VL minus 1 minus VL plus n minus VL minus n is equal to 0. So we want to end up with this thing here, and for our case it's not 0. on the right hand side it's equal to something that you find out on your own. So the main question is, well, how does this translate into a matrix equation? And on page 190, they explain that this can be written in matrix form as AB equals B, where the matrix A has dimensions m times n times m times n. So the matrix A is huge, and B and V are both vectors that are m times n in length and have one column. So now the question is, how do I translate between VL and Uij? For example, if I have L equal to 10, so V10, which Uij does it correspond to? Does it correspond to U12 or U23? How do I translate between these two? And this is a question of lexicographic ordering, which we will talk about in the next video. So read page 190 to 191 and read it again and again and again, and very soon you'll get it.